randomness. Are you convinced?
That's right.
Good morning, everyone. My name is Simon Pryor. I'm the CEO of MAV, and we've embezzled all the money, and we're going to take it and go away. Okay? Thanks very much. Okay, my name's Marty Ross. Simon is out of action. He's got an even worse hit than me at the moment. It's delightful to be back here again for the museum for another year of the lectures, and our first one, as you can see, is the problem with probability. Of course, the first problem with probability is what's the probability that anybody could find the new theater? So congratulations all for you on that. For those of you who are not on our email list, please put down your email and we'll get you on our list. Our next lecture is in 2 weeks. That'll be me on Egyptian mathematics. But for today, please welcome Burkhard Polster and the problem with probability. Thanks, Marty.
Right, so welcome all. Problems with probability. Well, let's get straight into it. You're all experts in probability. You may not know this, but you're actually experts in probability, experts in dealing with uncertainty. Like in everyday life, you pass somebody on the street, driving in the car, somebody's in front of you, pass them on the left or right. You're making judgments based on that person not going crazy at a particular point in time. Right? Everything is based on uncertainty in our lives, and we're making pretty good sense of it. Otherwise, you wouldn't be here; you'd be long dead. Right? So you're dealing, or you've got mechanisms that allow you to deal with uncertainty very well. But it turns out that in many situations, these mechanisms also mislead you. And a lot of what I'm going to talk about today is all about this, being misled by things that usually work very well, but in certain situations it doesn't work well at all. So first thing I'm going to do is tell you a little bit about probability. So probability and statistics, they're kind of mentioned in the same breath, and maybe it's useful to just say one sentence about one sentence about the other. What's the difference between the two? So what's probability? Probability makes mathematical sense of experiments or processes that are not predetermined. So there's a couple of possible outcomes, and those possible outcomes have certain probabilities. It usually goes from 0 to 1. The probability is associated with one of those events. 0 meaning can't happen at all. 1 meaning, well, it's definitely going to happen. And everything in between is different measures of certainty. And so probability deals with these processes and tells you, basically, if you have a process like this and you've got probabilities associated, what can you tell about the future of these things? The statistics is kind of the flip side. So probability is kind of looking into the future using mathematics. Statistics is the flip side, where how do you figure out those probabilities? Where you look at past events where these experiments get repeated a couple of times, and then based on the outcomes, you assign certain probabilities to these outcomes. So it's kind of looking into the past, one is looking into the future, and that's, in a nutshell, what the difference between probability and statistics is. Now, I mean, usually when you don't do this for a die, right? I mean, you want to figure out what's the probability for a 1 coming up. There's different ways of doing it, right? You just look at the die and you see 6 faces, and none of the faces is distinguished between the other ones. You throw a die, it's definitely going to land on one of them, something's going to come up. So basically you've got 6 different outcomes, they should be all equally likely. So in this case, to figure out what the probabilities are, we just say it's a 1 in 6 chance. It's a 1 in 6 chance. Text lotto. In many cases you can actually make up these dies that tell you kind of at a glance what the probabilities are. So you don't really have to run these experiments, you don't have to do the statistics. You kind of see at a glance what the probabilities should be like. So for text lotto is another example. So if you all played text lotto, right? You've got your 45 numbers, pick 6, right? And you win. No, you don't. When you think about it, well, there's lots of different choices for your 6 numbers, right? In fact, there's 8,145,060 choices for your 6 numbers. And none of these is distinguished between the other ones. So again, you basically got a huge die. It's got 8,145,060 faces. And when you play text lotto, well, somebody is rolling this die and one of the combination comes up. So you could actually play text lotto this way. You've got this huge die, and there's these combinations on the faces, and you sell tickets just as usual. And if one of those faces comes up, you win. There's another one. It's your probability of your birthday being today. Probably 0, because you probably wouldn't be here on your birthday. Right? But well, that's real dedication. All right, but basically again dealing with one of those dies, like 365 or 366 faces. We're rolling this thing, and that's the probability of your birthday being today. What else have we got? Probability of 2 coins coming up. Again, you can make up one of those. So we've got all the possibilities here. So 4 possibilities. One of them is both queens, so it's going to be 1 in 4 probability. So a quick introduction to probability. How do you get these probabilities? So I mean, in the first instance, you're trying to come up with a kind of a simple setup like this that shows you at a glance what the probability is. Okay, now, as I said, we've got these inbuilt mechanisms that tell us. In most instances, when we sort of go around, what's the chances of something happening, what's the chances of it not happening. We've got very strong opinions on these things in most instances. We're basically experts in this, we're doing this all the time. But it's easy to be misled. So I'm just going to show you a really, really famous example. And just in case I'm going to ask a question about this, just in case you've heard it before, I'm really just asking the question to those people who haven't heard it before, okay? So hold back, right? So just in case you've seen this before, hold back.
All right, now, let's give Ben a chance for some extra credit, shall we? We're going to call this the game show host problem, all right? Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, ghosts. Which door would you choose, Ben?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a ghost. Now, Ben, the game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2?
Right, so that's the problem. So who's heard this before? Who's heard this problem before? Okay, well, so it's a very famous problem in probability, and it came up. Well, it's about 30 years old, I think, but it really came up very prominently in around 1990 when somebody wrote about it. So this is Marilyn Bon-Savant, and she's supposed to be the smartest woman in the whole wide world, with an IQ of 200 and something, according to the Guinness Book of Records. And she writes a question and answer column in the Parade magazine, It's been going on for ages. The Parade magazine is one of those inserts that get inserted into newspapers all over America, so get read basically by everybody in America. And so she answers questions, and she's got a huge following of people who really revere her. Right? And there was this one time in 1990 when somebody asked a question, and that related to this show here. It's the Monty Hall show. It's basically a game show, right? And you see that there's the 3 doors there, and behind one of them is a prize, and behind the other ones are really duds, right? And basically, Monty, the game show host, did roughly, something like what was just described. So anyway, the question was, and I'll just repeat it for you. You've got 3 doors, right? Okay, so let's shuffle. Or shuffle. So you've got 3 doors, and you point at one of them. Say, you point at this one here. And now the game show host is basically a robot. Doesn't really have a choice of what he has to do. What he does is he looks at the remaining 2 cards. And among those remaining 2 cards, or doors, there's definitely one that's not the prize, right? So we just choose one that's not the prize and show you. Okay? And now you've got a choice. You've pointed at this, but now you have an option of whether you want to stick with this or whether you want to switch over here. Right? So stick with it or switch over here. Right, now, for those people who haven't heard this before, anybody here who hasn't heard this before? Okay. Now your gut feeling, what does your gut tell you? Should you switch or should you just stick with what you have? What do you think? Stick? No, definitely. No, you've got this feeling that you've just, you got it right. It's slightly psychic, right? Okay. So that was the question. And in fact, they've done studies on this. And most people, when asked this question for the first time, their feeling is either stick or it shouldn't make a difference. So what's the probability of getting it right in the first instance? So if I just shuffle it, what's the probability of getting it right in the first instance? 1 in 3. Because we've got basically a 3-sided die, right? What we talked about before. We've got a 1 in 3 chance, right? So the question is, once the game host shows something to you, has that probability somehow changed, or can you somehow improve your chances? Well, Marilyn's answer is, you should always switch. You should always switch, and the probability will actually go up to 2/3 if you do the switch, which is, not what you expect at all in the first instance. Okay, now I just want to show you how you can make sense of this in a very simple way by basically setting up one of those dies. Let's just say we pointed door number 1, okay? Door number 1. Then the prize can be behind door number 1, can be behind door number 2, or door number 3 over there. All right? And now we'll just figure out what is the probability of getting the prize. So these are all equally likely, and it doesn't really matter which one I pointed or going to be the same sort of analysis, right? Whether I pointed number 2, number 3. Let's just stick with number 1. Okay, so let's just stick with what we have, right? So stick with our first choice. Stick with our first choice and see what happens, okay? So this scenario here, what happens? What does the game show host do? What does the game show host do? Well, there's 2 dots here, so you can just choose one at random and show it to you. So it shows it number 2. You stick with number 1, what happens? You win. Fantastic, okay. So you win. Okay. Now, what about this one here? Okay. We're pointing at number 1. Which door does the game show host open? 3. You don't switch. Do you win the prize? No. What about this one here? Do you win the prize? No, right? Point at this one here, game show host shows you that one here, you stick with it, you're definitely going to win the prize. There's still a 1 in 3 chance that you win the prize, right? If you don't switch. Now what happens if you switch? Okay, let's have a look at it. So in this case, game show host opens one of those 2 doors, let's say it opens number 3, you switch. Where do you switch to? 2. Do you win the prize? No. Okay, then this one here, game show host, which door does he open? Still 3. Where do you switch to? 2. Do you win the prize? Yeah, you do. What about here? Game show host opens number 2, you switch to number 3, you win the prize? Yes. There's a 2 in 3 chance of winning the prize. So that really works. Now, you know, I mean, some people have seen a movie, right? In the movie they say you should always switch. And at that point in time, people think, well, I really know, yeah, I would have probably done the same, or, you know. But really going back to 1990, when this column came out, and she said it was 2/3, there was this huge uproar. She got like hate mail, no end. You know, all these people completely disappointed that their hero made a huge mistake, right? Like 1,000 PhDs writing in, no, you got it completely wrong, right? Many professional mathematicians writing in, no, you got it wrong, right? Many Nobel Prize winners saying, no, it stays at 1/3, you know. So it's really a very confusing question. And I mean, just in case you don't believe this, you can actually go to a website where we can basically do the statistics of the whole experiment, right? So they've set it up completely automated. So what you do is you go to the website and you make your choice. If you make a choice, and then you've got a choice of then Monty is basically the computer. It's completely predetermined what Monty does. So the computer opens another door, shows you a dot, and then you switch or you stay with what you have. And down here they've got the statistics of how people have fared who've played this game. So among those people who've switched, 68% won the prize, and among those people who didn't switch, 34.8 won the prize. So that really very much reflects the probability that we just figured out. Okay, now just to show you an example of how confusing this gets, I've got another movie clip. There's a proud tradition in Bollywood movies to rip off everything that Hollywood does. So for example, there's Rambo, right? It's Rambo. There's also a Bollywood version of Rambo. This movie that I showed you was 21. There's also a Bollywood version of 21. I'm going to show you that one. And what I want you to tell me afterwards is how people got confused, okay, when they actually did the scene. It's pretty much the identical scene, just a Bollywood version.
Please be seated. Please be seated. Come on, Vikram. Yes. So today, we will study the theory of probability. और इसे समझने के लिए हम एक game खेलेंगे. The Monty Hall game. You know. So 3 cups A, B, C. 3 प्याले या इन्हें 3 दरवाजे समझ सकते हैं. अब किसी एक प्याले की पूछें. मैं एक कार रख रहा हूँ. 3 cups. 3 दरवाजे, किसी एक के पीछे एक गाड़ी है. इसे हम शफल करते हैं, शफल करते हैं, शफल करते हैं. अगर आपको कोई दरवाजा चूज करना हो तो किसे चूज करेंगे? Yes.
So I choose door C.
Aparna chooses door C. Door C. First choice. Aparna. इसे हम खोलेंगे नहीं. Monty Hall कहते हैं कि randomly किसी एक दरवाजे को खोला जाए. So let's open A. No car here. Probability के हिसाब से यदि आपको अपनी पहली चॉइस को बदलना हो तो आप उसे बदलना चाहेंगे या नहीं? Yes, sir. Yes, sir.
Daya.
So it says yes.
No, sir.
Aparna says no. Okay. देखते हैं Aparna सही है या सही? First choice. No car. The car is here. हमें हमेशा अपनी पहली चॉइस को बदलना चाहिए क्योंकि अक्सर देखा गया है कि पहली चॉइस जो है वो ज़्यादातर गलत होती है. Confused? Okay, follow me. Come on, come along.
All right. So, can anybody tell me what was slightly off with this way of presenting? What do you think?
He randomly had no equipment.
That's right. Yeah. So, I mean, the most blatant mistake was to lift up an arbitrary cup. Right? That's not what Monty Hall does. He actually knows exactly where the prizes are, he knows exactly where the dots are, and he always shows you a dot. With this sort of setup, anything could happen. Right? So I could actually show you the prize. And actually, if you do the probabilities for this sort of setup, it doesn't make any difference whether you stick with what you have or whether you go with the switching. So the probabilities are in both cases 1/3. But I mean, there's other things in here which are kind of weird. So first he kind of hides the car under the cup, right? So nobody knows which cup it is. Then he shuffles it. Right? There's no point of shuffling at this stage because nobody knows where it is anyway. But then he's got the cups labeled, right? So you can actually know which one was anyway, and then so probabilities can get confusing for some people. So just in case you're a regular reader of our column in The Age, we had something about the Monty Hall problem last week. Our main prize was a little kitten. We like cats, and we don't really like calculators in school too much. So the duds were calculators. And just in case you like the sort of stuff that I'm talking about today, so maybe you want to check out the column too. All right, let's play a game. I want to find out whether there's any psychic persons here. Okay. Oh, there's two. Okay. So we're going to play this game. It's a thumbs up, thumbs down game. So you all have to play. The way we're going to play it is, I'm going to turn around, okay? And I'm going to either turn my thumb down or I'm going to turn it up. And you're going to do it at the same time. And what you're trying to do is, you're going to try and predict what I'm going to do, okay? So we're going to be able to play this? So I'm going to turn around. I'm going to do thumbs up or thumbs down. You're going to also do thumbs up or thumbs down. And then whoever is thumbs up when I say thumbs up, you stay in the game. Everybody who gets it wrong is out, right? Then we keep on going and see who's the most psychic person in this room, okay? Shall we do it? All right, so you all have to play, right? So I'm going to turn around now. I'm going to turn around, and I'm going to make my first choice. Have you made your choice? Do you think you know what it's going to be? It's going to be, are you ready? Everybody's got thumbs down or thumbs up? Yes? Okay. I have my thumb down. Okay. Who was down? Who was down? Who was down? So all you people are still in the game, okay? Everybody else can't play anymore, all right? All the thumbs down people, you're still in the game. Ready? Ready for a second try? Okay, ready? Only the thumbs down people. Okay. Now I've made my choice. Have you made your choice? Do you think you know what I did? Okay, I'm still thumbs down. Who's got thumbs down? Oh, good. Okay, let's try it again. So only the people with thumbs down are still in the game, okay? Ready? So, let's see how good you are. So I've made my choice. Have you made your choice? Okay, I'm still thumbs down. Who's still thumbs down? Damn, these people are good. Okay, let's do it again. Ready, go? So I've made my choice, and my choice is, what is my choice today? My choice is, I'm still thumbs down. How many are left? God, these people are psychic, okay. Okay, next one. I make my choice. My choice this time is I'm thumbs up. Who got thumbs up? Okay, those two people are cheating, okay. We've got 1, 2, 3, and how many have you had thumbs up? Okay, well, let's do one more. Ready? Ready to go? How many? 1, 2, 3, 4, 5. Okay, next one. Thumbs up or thumbs down. My choice this time is thumbs down. Who's thumbs down? Okay, we've got one winner, and I think we had 6 or 7 right. 6 or 7 right. That's pretty good. So are you usually that perceptive, or do you have a history of being psychic? You don't think so? Okay. Right, okay. But anyway, so we've got one winner here, 6 right. It's pretty amazing, We definitely have a psychic person among us. Do you think you could do it again, if you play the game again? You think, no, you don't think so? What about somebody else? How did you go? When did you go out? First one. Do you think you could do better second time around? You think? With a bit of practice? Anyway. Well, let's just figure it out, right? So, do you all remember Mani? Do you remember Mani? No? Well, Mani was almost famous at the World Cup. the Soccer World Cup, because Mani predicted quite a few games, correctly, so he did really well. Well, maybe you don't remember Mani, but you may remember Paul. You remember Paul? Oh, okay. Right. So there's Paul, and he's got his own webpage. By the way, Paul died. Sorry. Paul died about a year ago. But anyway, so Paul was really good at predicting stuff. So he was kind of the psychic animal. But of course, what people didn't realize was that there was actually like 1,000 animals all around the globe making predictions. And when you just think about it, well, if there's 1,000 people making predictions, well, then half of them will roughly get it right the first time. Then half of those will get it right the second time. Then half of those will get it right the second time, and you keep on going like this, and eventually you get it psychic, right? It works every time. As long as the crowd is big enough who plays these sort of games, you get amazing results. You get streaks like nothing, right? And in fact, these sorts of things, they come up like all the time. There's cases of people beating the stock market for 15 years in a row. Well, you can do the maths, and you'll find out, well, they probably did it randomly, because there's 100,000 people playing the stock market. Somebody will beat the stock market 15 years in a row. There's streaks in sports, right? So where some person hits the ball like 100 times in a row. There's hundreds of people doing this sort of stuff. You expect these sorts of things to happen every once in a while. So every time you read something like this in newspapers, be wary, right? There's real skill there, but there's also probability, kind of just throwing up these runs, these streaks, and you don't really realize it.
$12.50, press return.
So this is one of the flying bombs that the Germans used in World War II to bomb London. That's the successor here, that's the V2. Somebody recently put up these impacts on Google Earth, and you can, it's the right sort of plugin, you can actually look at where these things landed. At the time, so end of World War II, that's when they were in action. These sorts of maps got printed in the newspapers in London quite regularly, and have a look at this distribution of impacts, and people were drawing conclusions about what this all means. Right? I mean, you've got these areas that are not affected at all. Right? So there's areas that are not affected at all. There's clusters here. There's clusters here. There's clusters there. So there's people made up their minds what to do with this. Right? So they made interpretations of this. And like one of the interpretations was, for example, all the German spies lived here, right? And well, they were probably going for this because there's a railway station there, or there's like a munitions depot or something like this. And maybe people who lived here moved there, right? Because they had a relative there. So this was the kind of things that happened at the time. Right? And then the question is really, well, there definitely seem to be patterns here, right? There definitely seem to be patterns here. But are they actually meaningful? The main question was really, could the Germans aim their bombs accurately? Right? Are the patterns that you see here the result of somebody being really good at what they're doing? Or are the patterns that you're seeing here something that you could expect from a random process? Maybe there's a drop them, right? And somebody actually did an analysis of this after the war. It's not very helpful, they should have done it during the war, I guess. And basically what they did is, they just had a look at the map and divided it up into a grid pattern. So 24 this way, 24 that way. This gives a total of 576 squares. And then you count the number of bombs, which was 537. And then you get an average of about 0.929 bombs per square. And the first thing that people think, when they hear this sort of figure, basically 1 bomb per square, they think, well, if it's random, there should be about 1 bomb per square, right? That's what people think, that's what should happen. And so this is kind of one conception about probabilities, about averages, if you have an average of 1 of something, then that shouldn't be the case. But that's actually not the case at all. Right? So if you do the maths, and that's the maths, I'm not going to go into this, you can actually make predictions about how many empty squares you would expect if it was just purely probabilistic, purely chance, purely just dropping the bombs wherever they go. You could make a prediction, right? You could make a prediction of how many squares with just 1 bomb you get. I mean, with 2 bombs, whatever. So let's just do the maths and see how it pans out. And here's the maths. So here we just predict using a mathematical model how many we get. So for example, 0 squares with no impact, we should get 226. It's about half, right? About half. What about the actual number of squares observed? Is 229. 1 impact, 211. It's smack on. Right? And 2 impacts, so that they really match up here. So that if it was just done by chance, you would get exactly the same kind of distribution that what you got in real life. So although you've got all these apparent patterns and non-patterns happening there, you could replicate the whole thing by just running a random process, right? So the most likely conclusion from all this is that the Germans couldn't aim at all, right? So they weren't really that good. And this sort of stuff comes up all the time, right? So this is a newspaper report from 2006 about some people developing cancer in the RMIT building. So it's like 13 staff with tumors, right? 13 staff with tumors. And I mean, the first time you hear about this, you immediately draw the conclusion, well, there must be something really fishy going on, like some mobile phone towers or, the vice chancellors poison the staff or something, because they want to do, redundancies don't work, so you have to poison them. Anyway, and then they send the statisticians in, and the statisticians say, well, actually, you get these clusters, just like we just got clusters with the bombs, right? You get clusters. I mean, you should expect this, right? And then it comes out a news report like this, but of course we all think, no, they're just trying to cover up things, right? There's something really fishy going on here, right? Something really fishy going on. But if you actually do the maths, you come up with things like this. I mean, just to come up with 13 tumors as a result of a poisoning or some kind of radiation. I mean, the radiation has to be huge, right? It's not just mobile phone towers, like a nuclear bomb going off somewhere, or it's really quite significant. And as I said, I mean, these sort of pseudo patterns that come up, mislead us left and right. And of course, it also goes the other way around. When we try to be random, we go terribly wrong because our instincts tell us that some certain things should occur and certain things should not occur. So let's just have a look at this. So what I did here was I asked somebody, actually it's an experiment that we do quite regularly at university, where students are asked to go home, toss a coin. If head comes up, then they're supposed to make up a sequence of 100 heads and tails. Let's make it up. Try to make it up so that it's as random as possible, right? So make up a random sequence of heads and tails, but without tossing a coin. The other half, the ones who actually get tails with the first toss, they're actually supposed to toss a real coin. Right? Now one of these is made up, and somebody's really trying to be as random as possible, and one of these is a result of a real coin being spun 100 times. So which do you think is the random one, and which do you think is the, what do you think, which one's the random one? Yeah, so the top one is the random one, and the bottom one is the not random one. So can we have a vote on this? Who thinks the top one is the random one? So be brave, be brave. If you really think the top one is the random one, put your hand up. If you think the bottom one is the random one, put your hand up. Okay, actually, yeah, the audience here is pretty educated. This one is the random one, right? This one is the random one. And you can actually, if somebody gives you this, it's quite surprising, right? Because you've got these huge patterns in there, you've got these blocks of H's, and you wouldn't expect those, but you actually have a much more than 50% chance of getting a run of H's or tails like this in 100 tosses of a coin. So you get these long runs. I mean, just try it at home. Just try it at home. Do 100 and see whether you can get these long blocks of H's in. Anyway, so it's very hard to cheat, right? So if a random student gives me their sheet, I can basically at a glance decide whether they cheated or not. People are very, very bad at cheating with probability. All right. Okay, we have to do this one. I've not done this before, but let's just see how good you are at cheating, okay? So I want you all to pick a number between 1 and 50, okay? But before you pick it, there's a bit of a restrictions. Both digits have to be odd, okay? Both digits have to be odd. It can't be the same digit, so 22 and something's out. So 15 would work, 13 would work, 17 would work, 9 would work. So just pick a number, right? Both odd and not the same. If you all got the number? Okay, so who got 37? Who got 37? No, not too bad. Who got 35? Who got something else? Oh, not too bad either. But anyway, you had a choice from 1 to 50. How random was that, right? Anyway, let's skip this one. Now all this was child's play so far, right? Child's play. Now we get to the really serious stuff.
There's no sign of any pathogen.
Sure.
Look for yourself. Nothing but healthy cells. But it's still duplicated in the protein. You know how unlikely that is.
How unlikely? What are the odds?
99.999 to the infinite.
Yeah, it seems like we're showing this clip every second time. It's just too good, right? What is 99? 99 to the infinite, what is that? What is 99 to the power of 1,000? What is that? It would be 0, yeah. But still be wrong anyway. Anyway, it's completely wrong, right? But it's actually a life and death situation here, right? Where they're kind of trying to decide whether it's actually safe enough to go out and mingle with normal people, or whether they've actually been exposed to some terrible thing that will wipe out humanity if they do. Right? So it's very important to get it right. Luckily, some aliens abducted them at the end, so they're out of the gene pool, right? So they can't do any more harm. But now let's imagine this. Let's imagine that you're all doctors, okay? Yeah? You're all doctors? All right, you're all doctors. And we're running a test for cancer, for certain kind of cancer. And what we know as doctors is that if somebody has a cancer and takes the test will come up 90% positive. Okay, so it picks up 90% of the cases that are actually positive. Then, if somebody has not a cancer, it also picks it up pretty accurately with 93%. Right? So that's pretty good odds, how you think, right? So now the question is, what's the probability? So you test a random person now, and that person tests positive. So what's the probability that that person actually has cancer? So gut feeling again, right? Gut feeling. Is it around 1%, 2%? Is it 100%? What do you think? So let's just say, is it less than 50%? Who thinks it's less than 50%? Who thinks it's more than 50% that they have cancer? Yeah? More than 50% have cancer? Okay, well, the thing is, this question doesn't make any sense at this point in time. Why doesn't it make any sense? Well, just imagine, we've got a very special kind of population. Maybe the population has no cancer at all. Say, I tell you, we're testing now 1,000 people who have no cancer at all. Right? So what's the probability that someone who tests positive actually has cancer? 0, right? Because we don't have anybody who has cancer. Say, we're testing 1,000 people who all have cancer. What's the probability that somebody who tests positive has cancer? The probability is 1. It really depends, and we really have to put this in as extra information, otherwise this doesn't make any sense. How many people we actually expect to have cancer in the whole population. So we put that information in. Say the overall probability of cancer is 8%, 0.8%. So let's do the math now, okay? So we've got 1,000 people here. What's 0.8 of 1,000%? It's 8. So these are the people who have cancer, the rest have no cancer, okay? Now we're going to figure out how many of those, so we test all of them, right? So how many of those are actually going to test positive? It's about 7, right? So 90% of 8 is about 7. So we've got, these are actually going to test positive here among those 8. And among the rest, those 992, how many are going to test positive? Well, the 7%, basically 7% of those, so it's about 70. So many are, so there's the ones who actually have cancer and have tested positive, and there's the ones who don't have cancer and have tested positive. So how do you now figure out this business here? Okay, so we need the probability that a person who tests positive has cancer. So how many people do we have who have cancer? We have 7 plus 70, that's 70 altogether, 77 altogether. Right? So to calculate the probability, what we have to do is we have to calculate 7 divided by 77. That's the probability. It's 1/11. So there's a kind of a 10% chance, right? 10% chance that somebody who is actually tested positive has cancer. It's very low. And believe it or not, a lot of doctors get this wrong. Right? They will tell you that the second one, the green business. They will tell you about the green business. They will also conclude that you're basically doomed to die. Right? So next time you take a test, and you get a really dire message, the first thing you have to do is you have to insist on the second test. So people get this wrong all the time. Right? So they see the 90s up there, and they think that should also be a 90 down there. But it could be anything. It just depends on the business up there. I'll give you another example here. That's who remembers who that is? Who is it? Yeah, it's a runner. It's a very famous runner. Ben Johnson. That's right. A very famous Canadian runner who was found out to have doped. And let's just make up one of those doping tests. So we've got a doping test that's 99% accurate when it comes to detecting doped people, and it's also 99% accurate when it comes to picking up that somebody hasn't doped. And now the question is again, what's the probability that somebody who tests positive on a drug test like this, or a doping test like this, is actually has doped? What do you think? It's a test. The test says the question doesn't make any sense. But that's what gets reported in newspapers. Right? The 99%, that's what gets reported in the newspapers. And from that, it's concluded that somebody who is doped, or somebody who is tested positive, has definitely doped. It's completely nonsense. Right? It's complete nonsense. The only thing you really need now is what's the percentages. And then you can do the same sort of calculation again as we did before. So in this case, we've actually got this many people who actually dope, this many who are innocent. We can figure out, what corresponds to the 99% at the top, which is 4.5, which is this business. And then we figure out what corresponds to those 99.1% here. It's just those 9 points down here. And then we do the same calculation and we find it's 1/3. So somebody under those odds here who tests positive has just 1/3 of a chance of actually having dope. So this basically can't make any conclusion. And it's a fact that a lot of people who get, basically condemned by society for having taken drugs or dope in sports are actually completely innocent. It's unavoidable. They're doing 100,000 tests like this every year. Whatever small the probabilities are, they're going to get it wrong. In some cases. And it basically ends their careers, right? So these things are serious. Now there's another observation here. I mean, have a look at this one here. What does it actually say? What we're saying here is the probability that somebody has doped if they're positive. That's the probability. That's how you would express it. Now there's something that looks very similar to this up there. It's this one here. That's the probability that somebody is positive if they have doped. So now if this kind of do it again. So somebody has doped if they're positive, or somebody is positive if they're doped. It sounds pretty much exactly the same to most people, right? It sounds exactly the same. And people get confused with the two, get very confused with the two. Basically take one to be the same as the other, but you can see it's not the same, right? This is 31%, this is 99%. There's no real connection between the two to start with, right? So unless you do the numbers, it's completely off to think that these two things are the same thing. And the confusion between those two probabilities has led to like huge miscarriages of justice. And I've just got two examples here. So just to kind of hammer away that there's really a difference. In some circumstances, it's very obvious to see that the probabilities are completely different. So for example, what's the probability that it's dark if it's midnight? What's the probability of that? It's about 100%, right? Unless you really got the lights on. Right? What about the probability that it's midnight if it's dark? Well, pretty slim actually, right? Because it's dark at 7 o'clock and then it stays dark until 7 o'clock in the morning. So sometime in between there's a chance that you've got midnight, but basically you can forget about it. Right? So there's completely different kind of probabilities here. Now very, very prominent cases where kind of confusion about those two has played a huge role is the case of Sally Clark in the UK. Does anybody remember her? No? Anyway, so what happened there was she had two boys, and both boys died of sudden infant SIDS, right? So both boys died of SIDS. And the police, upon learning this, arrested her and charged her with murder because, that sounded very suspicious, right? Both boys dying. And they called on an expert witness, and the expert witness, just imagine you're a jury now, I'm the expert witness, so the expert witness tells you that the chances of one of those, a child dying of SIDS is 1 in forget about it, right? And then the chance of 2 dying is 1 divided by forget about it times 1 divided by forget about it, which is about 1 in 72 million, right? So the chances of 2 kids dying is 1 in 72 million, right? And now, the prosecutor and whoever was in charge, they basically, the first thing they did was, the calculation is stupid in the first place because you can only do this sort of calculation if the deaths are really independent, but since they occurred in one family and the whole thing could be genetic, there's definitely not that probability, but anyway, let's forget about that part. Now the jury was led to believe that this is supposed to mean that this is the probability that there's 2 deaths if somebody is innocent, right? So from that, they now concluded that they put her in prison, right? So they put this person in prison here, and eventually she got out. Well, when you think about it, what they should really have considered is the probability of somebody being innocent if you have 2 deaths in their family, which is kind of the same as saying the probability that somebody has murdered 2 children, 2 deaths. That's 1 in 2 billion. Right? It's 1 in 2 billion. It's a lot less likely here. So it's a lot less likely that that's what they should have looked at, right? But they didn't. And they only picked this up like a year after the thing, and like the Statistical Society issued some sort of a statement saying, well, you got it completely wrong. You convicted this person on completely wrong grounds. So that was like one. So eventually she got out, but obviously she lost 2 boys. Plus she was put through all this, so she drank herself to death basically and died. So it's really the confusion between 2 different sorts of things here that's very prevalent. That's very hard to figure out. I get it wrong. If you face me with one of those 2 things, I tend to get it wrong. Whenever I have probability problems, I really have to kind of stand back myself because my gut tells me something completely different from what my maths tells me. Right? So I don't have a really good sense for good probability. So I have to be careful. Right? Then there's another one here, O.J. Simpson. You all remember him? Yeah. So what happened there was basically the state was building up a case against him by presenting 2 weeks of evidence that he abused his wife for years and years and years. Right? So it's really, really bad his wife. But then the defense guy came up with statistics which said, well, there's about 4 million wives who get abused every year in America, and only like 1,500 or something actually get killed. So that makes it a 1 to 2,500 chance that somebody who batters a wife actually kills the wife. it's very unlikely, right? So like, there's the state doing all this evidence about him being bad to his wife, but basically the defense attorney says, well, it doesn't matter, right? I mean, it's, what he's saying there is you can forget about it. There's no connection. But of course, what they should have asked is about the probability that a murdered, battered wife was actually murdered by the person who abused her. And that probability is about 90%. And that probability was never brought up in the court case. What happened to O.J. Simpson in the end? He was acquitted. Huh? He was acquitted. So it kind of goes both ways. Okay. Coincidence. I just discovered a comedian.
It was about multiple births, and a woman had given birth to naturally conceived identical quadruplet girls, which is very rare. And she said, the doctors told me there was a 1 in 64 million chance that this could happen. It's a miracle! But of course, actually, no, it's not, because things that have a 1 in 64 million chance of happening happen all the time. To presume that your 1 in 64 million chance thing is a miracle is to significantly underestimate the total number of things that there are. Maths.
Don't watch this guy with your kids, okay? This is the most harmless kid I could find. Anyway, so I could have talked about heaps and heaps of things here. I've just picked a couple. So here's a nice one. Coincidences, right? So it's again kind of us going wrong with probabilities. Coincidence, it's a miracle. The Melways. Does anybody still use the Melways, or you're on GPS? All right, good. Yeah. So if you still use the Melways, you may have come across this. You open it up, right, and you're looking for a place. And the place is always like in the crease, or on the outside somewhere, and I have to kind of go back and forth. It's just so annoying, right? It just happens all the time, right? It happens all the time. It's so annoying, right? There's actually a really good explanation in its probability. Let's have a look at this. This is the exact dimensions of the Melways, basically. And I just want to ask you, what's the chances of you pick a random point on this page. What's the chances of ending up in this on the fringe here, basically? What's the chances? What do you think? It looks, I mean, the inside actually looks a lot bigger than the outside. You could think, well, maybe a little bit less, or well, less than 50%. But actually, if you just cut this thing up in the right way, it's a bit squashed, the screen here, but if it's just in the right dimensions, all these rectangles are actually the same size. So you've got 4 rectangles in the middle, and 4 rectangles on the outside. So it's actually as much area on the outside as there's area on the inside. So you've got exactly a 50% chance of landing on the outside. So there's actually pretty good chances of ending up on the fringe, right? It's just probability. And it stays. It's just that the area kind of gets squished on the outside a lot more than on the inside. Now we have to do this one quickly. We have to do this one. It's a very famous one. Quite a few of you will have heard about this one. So again, I ask you, if you've heard about it, don't say anything. You've probably not seen it in action. You can actually do it in action today. It's the birthday paradox. Half of you have heard about this, yes? Birthday paradox? Okay. Goes like this. If you let's just do the experiment. Okay, experiment goes like this. I ask the first person here to stand up and say out loud their birthday, okay? Then I ask the second person, the third person, the fourth person. Now, if it's your turn, and you've heard your birthday already, you have to say stop. And we'll just see how long it takes until somebody says stop, okay? Shall we try that? So we just go first row here, and then second row, and then third, okay. Can you? So this was the 28th of September, the 7th of October, the 1st of October, the 16th of July, the 27th of August, the 16th of December, the 11th of February, the 28th of August, the 8th of May, the 24th of August. That's good, but we'll just keep on going until a person who actually has to say something. I mean, we're definitely going to win because you're there. We'll just keep on going until somebody who's actually turn it is to say the date. Okay, so what was 16th of March, 8th of February, 12th of June, 4th of July. Stop. 27th of August. Who had 27th of August? Okay, you're probably meant for each other. Okay, so how many people was there? There was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 people. 15 people. So, I mean, what are the chances of that, right? I mean, we've got 15 people, and there's 2 with the same birthday, right? It's quite amazing, right? I mean, you wouldn't expect that, I mean, if you haven't heard this before. And again, if you do the numbers, you actually find that these are the probabilities. So when you've got 25 people in a room, you already got more than 50% of a chance of having one of those coincidences. That's pretty good odds, right? And I've done this a lot in class and stuff. I've had the second person say yes. But it was because they were twins. It gets a bit more complicated. But I mean, everybody, the first thing you hear when you think, well, what are the chances here? You think about, well, what are the chances that somebody has the same birthday as me? Which is actually a completely different kind of question, right? So among 23 persons, the chance that somebody has the same birthday as you is 6%. It's completely different, right? So just give you an example of something like this. Here are the prime ministers accepting Julia Gillard. And we've got one coincidence here. It's the first prime minister up there, and that's Keating. That's the 25th prime minister of Australia. So pretty good. And also, we've got another one. These people die, so you can also do this with death dates. We can't do it here because you're still not alive. But we can do it with dead people. And there's another coincidence here, right? So even with dead prime ministers, we get coincidences. Okay, so very last thing I'll do, we're kind of, just quickly. How random is random? Shall I do it or not? Shall I do it? We still got time? Who's got to go? I don't think they're going to kick us out. All right? 5 more minutes? Okay, good.
Heads. 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 Heads.
I feel the spell about to be broken. Well, an even chance.
78 in a row.
A new record, I imagine.
All right. So he does, actually they keep on going up to about 156. So I just want to try this similar kind of thing. I want to see how many heads I can get in 10 tosses, okay? I need a volunteer. Can anybody volunteer for this? But I need an independent volunteer, but you can come anyway. So, and somebody who's not related to me. Okay, you can come out, please. So I've got a coin here. If you've got a 50-cent coin, you can also. Right. So I'm going to do the 50-cent coin, and we're going to try and do as many heads as possible. Okay. So we've got. I'm going to catch it pretty much like this guy. Okay. So we're going to do is heads. Did it once. No. I messed up. Heads. 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 Getting there. Heads. Getting better. Oh. No, messed up, sorry. Roll it wrong. Whoops. Okay, I think it's good enough. Thank you very much. So what's the probability of a coin coming up heads? Good. One toss. Okay, now if you meet somebody like me, I can actually force it to be pretty much 100% unless I'm a bit excited like today. Now, just this action that this guy did, to do this, do that, there's not a 50% chance of getting both sides. There's actually, if you start out with heads, there's about a 51% chance that you get tails this way.